This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Hello. Welcome. Topic today, logarithms. And before I launch into the maths of it, a few words. We're learning logarithms in calculus, but logs are older than calculus. They came before. So it must be possible to do it without calculus. And they are one of these things that arrived out of necessity. Here is the deal. Here's the little historical blurb. And you're not, it's just out of curiosity. If you may or may not have studied logarithms in high school, it's not high school in Australia. That's an American thing, but in school. And logs have a property that I'm going to write here. A times b. This is log of A plus the log of B. Now, remember something like that? A property of log? Maybe you do, maybe you don't. And logarithms were invented because of that property. And I have to explain to you why that property is interesting, why it's important, why it was useful. The untrained eye may not compute that, but look, what's going on here is that a product, A times B, is being transformed into a sum, log A plus log B. So the logarithm has this property that it will turn a product into a sum. And sums are easier than products. Okay? So if you go back to the 17th century, when people had to go out sailing around the globe in a sailing ship or boat or whatever, and they needed to map their location rather precisely, hopefully. Otherwise, you never know if you're going to go to India or to Central America, right? Where you're going to end up. Anyway, so you need to measure the position of the sun, and you need to measure angles, and these are very tricky measurements, and you have to multiply lots of numbers that are very long, many decimal places and stuff like that. And the people in the boat, they don't have, we today we're learning derivatives and etc., but bring yourself back 4 centuries, 5 centuries, and the deal here is that they could multiply. Multiplication was hard. Sum, maybe. So it would be great to have a tool that was able to turn a multiplication into a sum. And then they invented the logarithm. Okay? Here's how they did multiplications. In the ship, they had a table of logarithms. And on the left column here, they had numbers, like, say, for instance, A and B. And on the right, you had the logarithms of those numbers. Log A, log B. Okay, so let me show you how they did multiplication. They need to multiply A times B. So they looked up A here, and they looked up B here. Okay? The table, which they brought from England or from Portugal or from Spain or from wherever, shows you what the logarithm of A is and what the logarithm of B is. So those you don't have to work to find. It's like your calculator can tell you that. Then you can't multiply, but you can add. So you add log A plus log B. And you found a number. There's a number here. And this thing is saying that it's the same thing as a log of A times B. So here's what you do. You do log A plus log B. It's a number. Look for the number here. Is this 1.789? Look for 1.789 here. Found it? There it is. This guy is log A plus log B, which so happens to be equal log of A times B. And this is a table of logs. So what's the number that's opposite on this side? A times B. You see that? I need to find the product A times B. I don't do it directly. I use the table, add those, see where it lands me, and look at the number opposite. It must be A times B. Next page. Clever. Very ingenious. The guy who invented a log invented it because of this formula. He wanted this to be true. Okay. Later on, logs became important for other reasons. Okay, it's a case of survive. Okay? There was a time when it was not important to do these computations anymore, but the logarithm continued to be studied because it's important for other reasons. So we're going to leave it at that in terms of historical perspective, and we're going to take a look at the modern way to define logarithm. Let me ask you a question here. Have you learned, maybe before, that the logarithm is the inverse of your exponential? Some people may have, some people maybe not, and some people may have but forgot. Okay? It's the typical way of defining logarithm is first you get to the exponential. You study properties of the exponential like 2 to the power x. And then you define the logarithm as the inverse. Okay? We're going to do it totally differently. We're not going to do it that way. We're going to start with the logarithm and end with the exponential. Because, we're sophisticated people. Anyway, logarithms. So here's the deal. I'm going to draw the function y equals 1 on t. This is t here. This is y here. I'm not using the letter x for a reason. And there you go. This is the graph of y equals 1 on t. And I'm only doing that for t positive. I could do it for t negative, but at the moment, let's consider t positive only. And I'm going to fix t equal 1 here. One. So this height here is also 1, by the way. Because if you plug in t equal 1, y is 1. Now, give me a value for x. Huh?
Any value?
Positive. Give me a positive value for x.
3.
3. How much is log 3? I'm going to show you how much log 3 is. She said 3 for x. Log 3 is the following. From 1 to 3, look at the area in here. That area is log 3. And I'm going to not call log for log, I'm going to call it ln. Is that clear what log 3 is? I mean, imagine that you have a precision engineering instrument to measure areas. Okay? Forget about all of the calculus stuff that we're doing. You have a machine that can measure this area here. You draw this picture as perfectly as you can, and you measure the area from 1 to 3. That's what I want to call log 3. All right? So how much is log 5? Well, if you know how to do 1, you know how to do the other one. 5 is here. So you go all the way to 5, and log 5 is the area from 1 all the way to 5. Okay? If you had given me a number between 1 and 0, so a number that's smaller than 1, you can still do it. Let's say you give me the number 1/2. You can still do it. Go over there. This area here is going to be log of 1/2. But you have to be careful, because you're going from 1 to 1/2, I'm going to say it's a negative value, because I'm going against the usual direction. If I'm going that way, it's positive. If I'm going this way, it's going to be negative. All right? Convention. So it's a negative area if you want. Let's get mathy here. Let's write an equation for this. If x is a positive value, we write the log of x is the area from 1 to x, 1 on t, dt. Okay? I'm using the integral symbol to represent area. We are used to that. So this guy here, log 3, you could write it as the integral from 1 to 3, 1 on t dt. Log 5 is the integral from 1 to 5, 1 on t dt. Log 1/2 is the integral from 1 to 1/2, 1 on t dt. It's okay to use the symbol for integral to represent area, because we know it's useful for that. If you want, you can rewrite this, but this is just a cosmetic rewriting. It's not such a big deal. 1 to x, t to the negative 1 dt. Okay? So that's a log. Let's take a look at some properties of log now. Welcome. Which properties do we want? Let's see. I've already said a few properties. I'm going to write them down. They all have to do with area. But things we'd like to know are things like, okay, It's a new function. It's not a polynomial. It's not a sine. It's not a cosine. What's its graph? What's the graph of logarithm? What's the derivative of a logarithm? If we can, what's the integral of a logarithm? Okay? We would like to know these things. What are the special properties, like the one I wrote here in the historical note? Special properties that it has. We'd like to know these things. So property 1, if the x is bigger than 1, not only bigger than 0, but bigger than 1, then log x is positive. And if the x is between 0 and 1, then log x is negative. And you don't have to prove these properties here in this course. They are just common sense from here. If you go from 1 to a value x that's bigger than 1, it's a positive area. And if you go from 1 to a value of x that's less than 1, you get a negative area. So that's why it's positive here and negative there. It's what I have already discussed in here. By the way, log of 1 is 0. Because you're measuring the area from 1 to itself. So it has height, but it has no width, right? So, whoop, I dropped it. Area 0.
So if there is any other constant, will that be 0 again? Like logarithm of 3?
No, log 3 is not 0. Log 3 is from 1 to 3, 1 on t dt, and it has this picture here. 1, 3. It's this area, and that's a positive area. 1 is a special case. Okay? 1 is a special case. Here's 1, and I'm looking for the area. If you go from 1 to 1, I don't move. So it's just a thin line. There's no area there. Like when you see somebody walking and they're so thin, you think, oh, they don't have any volume. It's like that. Very thin person here. So let's see, from these properties here, I can kind of attempt a sketch of a graph of log. Here's x, here's 1. Now, when x is 1, the log is 0. So the graph goes exactly through here. If x is bigger than 1, the graph is going to be positive. That's not a true graph, okay? If x is less than 1, the log is negative. So, and of course, x is only positive, so you can never move to the left of his vertical line here. Of course, the picture is not going to be like that, right? The true picture is more like this. Okay? Okay, let's find the derivative of log. No, before we do that, let's go back to the real world here. You don't have this miracle engineering machine that computes the area for you. Okay? So if you want to know how much log of 3 is, how do you do it? You're stuck. Okay? You're stuck to do it. All right? Because there is no miracle engineering machine that will... Oh, there is. Sorry, your calculator. There is a miracle engineering machine, but forget about the calculator. We don't mean the calculator. Okay? Let's pretend you don't have a calculator. How would you compute log 3? Because people did compute log 3 and log 5 and log 20 before calculators. So it must be possible to do, and they did not have a miracle contraption that computed areas for them either. So how do you do it? It is possible, and that's why calculus is here. It helps you. Okay? It's even possible to do it without calculus, because it was done before without calculus. But it's better with calculus. All right? And there are formulas that will allow you to compute log 3. Approximately, never exactly, but approximately. And that's, for any practical purpose, that's what you need. Okay? And these formulas are the formulas that are put inside your calculator to do it. And that's where your calculator gets it from. Okay? So there's a whole theory of calculus that allows you to compute these logarithms, and that's put inside your calculator. Okay? No, it isn't. Now, stop lying. Right? What they really do these days is the following. Memory is so cheap that they simply put the table of log hardwire. They don't compute. So whenever you press log 3 in your calculator, the calculator is not actually computing log 3. It's just reading off a table, which is the most sensible thing to do, really. But if you were in a situation where you can't have really a lot of memory, then it is possible to program the formula into the calculator, and the calculator would then compute the value of log 3 for you, okay? And early calculators, I think, when memory was very expensive, they did that. And what happens if you type in a value like log of 7.21890345? It's going to be a very lucky day if that logarithm is tabulated in your calculator. So what the calculator does is it looks at the two nearest and interpolates. Okay? That's how it's actually done. For us, we're just going to admit that if you need to compute log 3, you type in the calculator and the number comes out. And we're going to be happy with that. Okay? Okay, so the question here is, what's the derivative of log? And the answer is this. Elegant, right? Very elegant. Very elegant. I'm going to show you that in a sec. It's already written on the board, but it's a fundamental theorem of calculus. It's a fundamental theorem of calculus. Okay? The fundamental theorem of calculus says sorry, says that if you integrate a derivative, you go back to the same function. And if you take a derivative of an integral, you go back to the same function. That's what the fundamental theorem of calculus says. So if you take a derivative of a log, What's the log? The log is that integral there. You go back to the function in here. The function in here is 1 on t, but you're evaluating it at x, so this is 1 on x. Okay? I'm going to give you another justification. Okay? What's the definition of derivative? Log x, take a derivative, that's the limit. Whoa, we're going back to limits. When h goes to 0, log of x plus h, take away log of x and divide by h. Why, George, are you going back to limits? Well, we have a new function. When you have something new, it often is a good idea to take a look at the original definition. Okay? Of course, we want to avoid this as much as possible, but this one is new, so let's take a look at it. I want to take a look at what this is. This is 1, this is x, and this is x plus h. Log of x plus h is the area if you go from 1 to x plus h. Log of x is the area if you go from 1 to x. So this difference here is this area here. Does that make sense? The numerator is the area in here. I'm going to make h go to 0. So this is going to be a very thin area. Okay? If this area gets to be very, very thin, it's going to be almost like a rectangle, right? Base times height. Height and base. The top is not flat, but it kind of almost. Okay? What's the base? The base measures h. And what's the height? The height measures log x. 1 on x. Beg your pardon, 1 on x. So this area here is approximately base times height. So the number in the numerator is approximately h multiplied by 1 on x. So this is approximately limit when h goes to 0 of h multiplied by 1 on x divided by h. The h's cancel, and you're left with 1 on x. So I gave you two explanations of why the derivative of a log is 1 divided by x. I have something else to point out to you. We just filled a gap in our knowledge. Okay? Something we didn't know before, but now we do. The gap. Remember the power rule? The power rule for integrals says that if you integrate x to the power n dx, what do you get? Plus 1 divided by n plus 1 plus constant. And that rule was valid for any values that you put in here on the exponent, except -1, because you can't divide by 0. So this formula is good, except if n is -1. And I didn't give you any formulas for when n is -1. So you don't know how to do this. Which is, of course, the same thing as this. But now you do. It's the log of x. For x positive. There's no work in here. It's a consequence of the way you define the logarithm. You said the logarithm is the area under the graph of 1 on t. And so the integral of 1 on t, or the integral of 1 on x, has to be log. Because integrals are areas, remember. And antiderivatives are related to integrals. I'm going to write the next line in red. Extremely common mistake. People who need to do an integral, and they forget that when the exponent is -1, the formula is different. So they have to do x, say, to 2k plus 3 dx. So they go there and write, it's x to the 2k plus 4 divided by 2k plus 4 plus constant. You add 1, right? That's what I do. This formula here is saying add 1. So it doesn't matter what's in the exponent, add 1. 2k plus 3 becomes 2k plus 4, 2k plus 4. That's fine, as long as 2k plus 3 is not -1. And what if it is -1? Then the answer is log. Okay? So in here, you have an option. You only use that if n is not -1, and you only use this if n is -1. Okay? Very common mistake. Okay, so let's see. Just for your information, the log that we are studying, there are different logs in this life. There's a log base 10. There's a log base 2. Your calculator has the log base 10 in it. And there's a log base e. This is a log base e. Okay. The math people like the log base e. The engineers, they like the log base 10. The computer scientists, they like the log base 2. Okay? To make matters a bit more confusing, we don't write ln, we write log. So if you're reading a math book and you see log, it's base e. If you're reading an engineering text and it's written log, it's base 10. And if you're reading a computer science text, it's going to be base 2. Okay? Be careful. Be careful. But enough of that base thing. I didn't tell you any. This was a footnote. Forget that. I didn't tell you what the base is, really. Okay? Properties. More properties. So I only gave one property. Let's put 2 here. Log of A times B is log A plus log B. Here A and B are positive, right? And this is a property about areas, okay? This really is a property about areas. Here's 1, and here is A times B. So the left side, the log of A times B, is this area here. Okay? And we're saying that you can break this area in 2 bits, a log A bit and a log B bit. Here's 1 again. Here's still the A times B. And here's the A. Log A is the area from 1 to A, so it's this. So what you're saying is that the area from 1 all the way to A times B, you can break it into the area from 1 to A, plus the leftover. The leftover is this. This is a leftover. It's the area that goes from A to AB. And it turns out, by a very neat trick having to do with change of variables in the integral, that this is numerically equal to log of B. Not obvious, eh? It's a neat trick. It's a problem in the book, a solved exercise. We're going to do it in a tutorial. Okay? Not today. And so log of A times B is log of A plus log of B. I find it very surprising that properties of log that I used to find absolutely horrible when I was learning them for the first time, before university even, in fact, having to do with geometry. They are properties of areas, if you study it this way. Property 3. Log of A to the power B is B times log A. Here A is positive and B can be any number, positive or negative. Doesn't matter. Again, it's a property about areas. I'm not going to draw a picture here, but that's what it is. So log continues on its great tradition of turning something complicated into something simpler. Okay? In property 2, it turned a product, a multiplication, into a sum, which is simpler. In property 3, it turns an exponentiation into a product, which is simpler. Log has all these wonderful properties, making complicated expressions a little simpler, except that you don't deal with A and B anymore. You deal with B and log A. So for instance, if I need to find out log 4, well, this is log of 2 squared. This is 2 log 2. So if I want to find out log 4, I just need to find out log 2. It's a great help in building the tables, right? If I need to find out log of 1/4. Now let's write it not as cramped. Log of 1/4, that's the same thing as log 4 to the negative 1. So it's negative 1 times log 4. So it's negative 2 log 2. Okay. Oh, if only we knew the value of log 2, right? You'd be able to find all of these other logs. Log 6 is log of 2 times 3. Right? So you need log 2 and log 3 to be able to do log 6. Okay? Log 6 is log of 2 times 3, log 2 plus log 3. So you need to know log 3 as well as log 2 to get log 6. Well, can't win them all. Here is a useful formula. 2 useful formulas, in fact, having to do with derivatives. You give me a function. I'm going to call it f of x. And then I produce the log of f of x. So here's an example. You could give me the function f of x is x cubed plus 2x squared plus 1. And then I take the log of that. Log of x cubed plus 2x squared plus 1. And the question is, what's the derivative of that? You have to use the chain rule here. Okay? And it tells you the following. I can call this y. So dy dx is the derivative of log. The derivative of log is 1 on x, right? Log x gives you the derivative of 1 on x. So what it says is that if you want to take a derivative of a logarithm, you look at the thing that's inside and do 1 divided by that. Okay? So this is 1 divided by x cubed plus 2x squared plus 1. And then, using the chain rule, don't forget to take the derivative of the stuff that was inside. So let's multiply that by 3x squared plus 4x. Okay, look. It is not such a complicated rule. You just have to remember a little thing, but it's not such a complicated rule. All you need to do is get the stuff inside the log and put it in the denominator, and then take a usual derivative of the stuff that's in here. The general formula is this. You take a derivative of that stuff inside the log and divide by whatever is in there. Okay? And it's a chain rule. that gives you that formula. So let's take a look at another example here. If you want to take a derivative of log, what this is saying is, this formula is saying that you have to divide by what's in there, and in the numerator here, you have to take a derivative of that. So this would be, you'd finish the problem after you perform the operation in the numerator. Is that okay? All right. Let me show you a little trick. Before you take the derivative, take a look at this. This is the log of x squared plus 1 to the power 1/2. And log has a beautiful property when it comes to exponents, right? The 1/2 comes out multiplying in front. This is the same thing as 1/2 log x squared plus 1. So you got rid of that square root. Okay? That square root went away. You cannot simplify this. Oh, George, you do have log of x squared. Yeah, but I do have that nasty plus 1 that just doesn't make it right to simplify any further. You cannot bring this 2 outside multiplying, okay? So this one is stop there. But you can take this square root out by interpreting it as a power. And now, this was before you took the derivative. Now you take the derivative on this expression, which is equal to that, which is equal to that. And you're going to have an easier time when you come to this. Okay? So let's take a derivative of that. Derivative of this, 1/2 multiplying in front, it's just 1/2. Now take a derivative of log. It is going to be x squared plus 1. And in the numerator, you got 2x. The 2's cancel, so it's x divided by x squared plus 1. Okay? Notice that by using a property of a log before you take the derivative, I made the derivative easier. Is that all right? If you don't use the property here, it won't be wrong, but you're going to have to do the derivative with a square root in here, which is a harder derivative to do. Okay? So you're allowed to do what I just shown you there. Okay. Two more things before we have a break. I gave you this formula here. X positive, right? What if x is negative? Let's take a look at this. 1 on x is this. But you can do you can only do log if x is positive. But you can do 1 on x if x is negative, and it has a graph like that. It's perfectly all right to do 1 on x if x is negative. Okay. So this is okay if x is positive, but what is the formula if x is negative? What's the integral of that guy if x is negative? And it turns out that if x is negative, from the symmetry of the picture, okay? This is all right. It's a log of this quantity here. The x is negative, and I put a negative in front, so it's a log of a positive thing. There's a double negative here. One that you see with a negative, and one that's implicit in the fact that the x itself is negative, okay? So there is a double negative. This is a log of a positive quantity. And what you're going to see in your book, and what you're going to see in any maths book, or engineering for that matter, is the two formulas combined like this. A formula that works for x positive and for x negative at the same time. That symbol is the absolute value. So if the x was already positive, it's just x. And if the x is negative, it changes the sign to become positive. Okay? That absolute value there is no big deal. It's just to make sure you're taking the log of something positive and incorporating these two formulas together. Okay, let's take a break, and when I come back, I'll give you the formula for the integral with logs, and we'll talk about the exponential. Let's take 5.